Alright, we're going to be working with stretching and reflecting transformations on graphs. And if you're following along in Stewart's calculus, we are in section 1.3. And so I've plotted here the graph of f of x is equal to x squared. Now if I multiplied f of x, the entire function, by a number, let's say this number is c for constant, then the graph is going to stretch vertically by a factor of c. So you're going to get a new graph, and it's going to be stretched like this. So it's going to go from the red graph to the green graph by a factor of c. By a factor of c. Notice it still has the same vertices right here. Okay. Now, if I multiply the entire function f of x, the entire thing, by a number between 0 and 1, so I could write that as like 1 over c. For example, 0.5 times f of x, or 0.25, a fourth, times f of x. Then the graph actually shrinks vertically, or vertically compresses. So it gets a wee bit fatter. Yeah, like that. There's it shrinking. Bam. So the red graph shrinks by a factor of, well, I could say that it stretched, I couldn't say it stretched. Well, I guess I could say it stretches by a factor of 1 over c, but that's a shrinking, so I could say it shrinks by a factor of c. Shrinks by a factor of c. Alright, now that's vertical. Anything where you have a constant, being multiplied, or a function being multiplied by a constant, and that's outside of your argument. Remember, I like to call this the argument of f, function f. X is our argument. So if our entire function is being multiplied by a constant, or divided, you could say this is divided by c, but it's really being multiplied by a fraction, 1 over c. If this is the case, and our constant is outside of the argument, then it's vertical. It is a vertical transformation. I'm just going to write it here for all y'all. Alright, now, what if we multiply c what if we multiply c inside the argument? Or what if we divide the argument by c? In other words, multiplying by 1 over c, or argument over c. Then that would be a horizontal stretch and compression. And for example, what if I have f of x, actually f of c times x. Okay, multiplication of a constant inside the argument of the function. That is a horizontal shrinkage or compression. So if red is our starting function, and it shrinks horizontally, then that's in red. I probably shouldn't have wrote that in red. Hold on. Let's make it better. Let me do yellow for C. So now it's a shrinkage. It's basically going to be the same as this green one here, except it's not really vertical, it's horizontal. So you think of it this way, bam, like that, bam to the yellow, like that. So that would be f of c times x, and that's shrinking by a factor of c. Excuse me. Now, if you're multiplying inside your argument by 1 over c, then essentially you get x over c. You're just dividing by c, and that has the opposite effect of what you probably would normally think. That's basically this seal cyan color right here, it is a horizontal stretching by a factor of c. So think of it like this. The red is our original, okay, like that. Alright, so that would be stretching by a factor of c. Alright, so also we can do reflections, and for this actually I'm going to do a new graph because that was just really messy. And I want to do a different graph. I want to do the graph of f of x is equal to x cubed. So this is f of x is equal to x cubed, an odd function. So now if we multiply the entire function f of x, if we multiply the entire function by -1, we get a reflection about the x-axis. And this, excuse me, this is the x-axis. You better know that. It's like second grade stuff right there. So it means it flips this way. It flips around the x-axis. Not like this, but this. So how do we write that? We write it like this. And interestingly, alright, this goes like that, and this goes like that. So interestingly, we have the graph of x cubed here. Its reflection about the x-axis is the same as its reflection. It looks the same as its reflection about the y-axis. So I probably should have done a different function. But I'll do a different function after I do this one. So you have to multiply, to get the reflection about the y-axis, you have to multiply your argument, everything in your argument, by -1. Just make it a negative, wherever it is. If it's x, make it -x. And so that's a flip in this direction. Which, when this is flipped that way, you're going to get this yellow graph again. See? So let me do a better function. So we know that this is a flip around the x-axis, and this is a flip around the y, I'll do it in red, axis. Oops, that's still blue. There. Okay, so here's a coordinate plane, and I'm just going to draw a random graph. So sure, kind of looks like a really fancy N. So a flip around the x-axis, if we multiplied this, the equation of this graph, everything by a negative, we would flip it around the x-axis, and we would get it's called a reflection, so it's going to reflect each other about the x-axis. So this is negative f of x, and I'll just say this is f of x. And now, if we multiply all the arguments by -1, we get a reflection around the y-axis, like that. So remember, cyan is our original. So I'll do this in red, and around the y-axis is a reflection of the y-axis. Like that. Might be kind of hard to see with the yellow graph on there, but if you can, just try to look at this and this, ignoring the yellow, and can you see how they are reflected about the y-axis right here? So that's it for reflections, and I will do problems related to this in a future video.